This webinar. Today, since you already know, the topic is about Ansys HFSS, 30 minutes of high frequency simulation for band pass filter. And so before we go through the simulation demonstration, let me talk about the Ansys Electronic products. We have 9 products for electronics. The first one is Ansys HFSS, which I'll be talk more later. Second, we have Ansys Maxwell. It's for electromagnetic design and simulation tool for low frequency application. We also have iSpec. iSpec is a computational fluid dynamics CFD solver for electronics thermal management. We also have Sherlock. Sherlock provides live prediction for electronics hardware. We also have MotoCAD. MotoCAD is a template-based design tool for multi-physics analysis of electric motors. We also have SI-Wave. SI-Wave is a power and signal integrity simulation and EMI analysis. We have EMA 3D cable. It's an electromagnetic compatibility modeling tools that specialize in analyzing lightning-induced electromagnetic effect on large platforms such as aeroplanes. Then we have a NUHETS filter solution. It is an automated radio frequency, microwave, and filter design, synthesis, and optimization. Lastly, the Q3D extractor. It calculates the parasitic parameter of frequency-dependent resistance, inductance, capacitance, and conductance for electronic products. So for Ansys HFSS that we're going to demonstrate today. What's an HFSS? HFSS is a high-frequency structure simulator, which is a general-purpose full-wave 2D or 3D electromagnetic design and simulation tool for high-frequency application. So what's a high-frequency application? High-frequency application is such as antenna, microchips, filters, integrated circuits, printed circuit boards, PCB, radio frequency components, and microwave components. So for HFSS workflow, this is inside the HFSS project manager. So firstly, the 3D components, model, and circuit element. This is for the model design tools with materials. Next, after we create the 3D design, we need to add the boundaries to specify the field behavior at the edge of the problem region and object interference. After that, we're going to add assign excitation to specify the sources of electromagnetic fields, charges, current, or voltage. And then we set up the mesh operation. We set up the simulation design in analysis. And after we simulate it, we can see the post-processing the result inside all these 4 results for display, field overlays, and radiation. So for this optimetrics, I won't cover this in the webinar because this is an extra simulation tool and it needs a different license to do that. So for the solution types, the solver, we have 6 solver here, which is the HFSS, the default solution type for high frequency design. Then we have HFSS with hybrid and arrays. it adds the ability to define hybrid region and arrays in the HFSS design. And then we have transient it is used to calculate the problems in time domain. Transient solutions are applicable for simulation involving pulse excitation, like lightning strikes. And then we have SBR plus. It uses the Savant shooting and bouncing ray, SBR, technology to calculate the far field from the current source and define geometry via one-way coupling. Example of uses in antenna. And then we also have an eigen mode used to define the resonant frequencies of the structure and field at those resonant frequencies. It can be anything for high frequency. And also the characteristic mode used for calculating characteristic mode of a structure. The structure can be metal, conductor, or dielectric. Next, for the boundaries, we have all these boundaries here, and all these can be used in the HFSS model. I will show you how to assign the boundaries during the demonstration. Next, for the excitation, these are all the excitation that include in HFSS, the wave ports, lump ports, and all this excitation, current source, and voltage source. The most common one and the most used one is the wave ports and lump ports. I'll be showing you how to assign the excitation on the demonstration. Next, the mesh operation. We have on-selection length-based mesh, on-selection skin depth based, inside selection length-based curvilinear meshing, model resolution, surface approximation, and surface parity for tau. And for the processing, we can plot the scattering parameter, the S parameter result, via using rectangular plots, polar plots, vector tables, and Smith charts. We can also plot the field result of the model, such as for electric field, E field, magnetic field, H field, the current density, which is the J field, then the quality factor field for eigen modes and others. I'll show you the others during the demonstration. And also we can create an animation for the field result for the mesh and for the geometry. This is one of the example of the animation. You can see the electric field here is moving. So next, for better understanding what is a scattering parameter, I will be showing you a video on what is an S parameter. Enjoy the video.
Let's start by explaining what we mean by a network. In the radio frequency world, a network is a device that has one or more ports, with each port being able to pass, absorb, and/or reflect radio frequency energy. An example of a one-port network would be an antenna or a dummy load. Common two-port networks include things like filters or amplifiers, and a three-port network could be a device like a directional coupler or mixer. 1-, 2-, and 3-port networks are the most common, but networks with higher number of ports also exist. We can analyze these devices, or networks, by injecting RF energy into a given port and measuring the level of RF energy that appears both at that same port, that is, the reflected power, and in the case of multi-port devices, at the other ports. Except in some very special cases, usually only one signal is injected into one port at one time. And in most cases, our network will exhibit frequency-specific behavior, so measurements are normally made over a range of frequencies. In most cases, networks are analyzed using instruments called network analyzers. The most common way of representing these quantities is something called S parameters. The S stands for scattering, since we're measuring how much RF is scattered back from and out of the various ports. S parameters are named using the capital letter S followed by a pair of subscripts. The first subscript is the port where the energy emerges, and the second subscript is the port where the energy enters. For example, if we measure the amount of power passing through a two-port network, this quantity would be referred to as S21. The amount of power reflected back on port 1 would be referred to as S11. Let's give a more complete definition of S parameters for a two-port network. A two-port network will have 4 S parameters: S11, S21, S12, and S22. S11 is the amount of incident power that's reflected by the input or forward port. S21 is the amount of power that's passed from the forward to the reverse port, and S12 is the amount of power passed in the opposite direction. The last S parameter, S22, is the power reflected from the reverse port. These S values can be defined as ratios of the power seen at each port. There are a few other useful things to know about S parameters. First, S parameters are sometimes represented in the form of square n by n matrices, where n is the number of ports. For example, 1 port, 2 ports, and 3 ports. It's also important to remember that S parameters are complex values consisting of both a magnitude and a phase. The reflection coefficients, such as S11 and S22, are often plotted on a special graph called a Smith chart. And one of the main advantages of using S parameters is that S parameters of individual devices can be cascaded together to predict the overall performance of a system. Although S parameters are almost universally known among RF engineers, there are also more common or conversational terms for some S parameters. The reflection coefficients S11 and S22 describe the impedance match for input and output. This is usually quantified in terms of return loss or voltage standing wave ratio. Please see the presentation Understanding Viswar and Return Loss if you'd like to learn more about these measurements. For transmission coefficients, S21 corresponds to the amount of gain or loss between the input and output ports. S12 is a measure of reverse isolation, or how much power is flowing the wrong way through a device. For example, an amplifier should have gain in the forward direction, that is a positive value for S21, but ideally 0 power flowing back from the amplifier output to the amplifier input.
So that we know already what's an S parameter. Now let me show you what we're going to simulate after this, which is the bandpass filter. So before that, what is a frequency filters? The definition for the frequency filters in signal processing. Filters are used to remove some unwanted components or features from a signal. A filter extracts important frequencies from the signal that also contain undesirable or irrelevant frequencies. You can see there are 4 types of frequency filters. It has a low pass filter, which allows only low frequency. This is all the gain versus frequency graph. You can see for the low pass filter, it allows only the low frequency to pass through. Then the high pass filter, it allows only the high frequency to pass through. And then the band pass filter allows the middle, the between low and high frequency to pass through, and the band stop filter, which allow only the low and high filter at low and high frequency. Now, for the what's the application in using this filter in signal processing? So I'll be showing you a video on what's the application for the in signal processing.
What is signal processing? Signal processing is a branch of electrical engineering which pulls meaning from the broad sources of data that are all around us. But what does that mean exactly? It means signal processing is at the heart of our modern world. Signal processing powers modern communications,
How can I help you?
modern entertainment, and tomorrow's transportation. Signal processing is at the intersection of biotechnology.
Voice print access.
Access granted.
It's in our social interactions, learning to anticipate our needs and emotions, helping us hear the world around us and to better understand it.
سلام چطوری خوبی؟ Hi, how are you doing?
To bring new life and help us heal. Signal processing brings the world to our homes, adds clarity, and puts it in our pockets. Signal processing documents our cherished memories, helps to keep us safe, and powers the world of finance. Signal processing, processing the future.
Now that we know the application of signal processing in the world, let's go through the demo together. So as we all know, the demo will be a bandpass filter model. A bandpass filter allows frequencies of a certain range to pass through, but attenuates those frequencies outside the bandpass range. The figure below here is a model of a bandpass filter and a volume of air surrounding it. The color represents the electric field intensity here, the color contour here around the conductors. The varying gap between the resonator is the bar here, the 8 bars inside this bandpass filter, and the alternating axial offset of each resonator produce the desired bandpass filter behavior. So in this simulation, I'll show you how we familiarize with the HFSS design environment, how to create a 3D geometric model, assign the excitation, analyze the model, and review the social data. And for the post-processing, we'll be plotting the S parameter using a rectangular plot. We plot the electric field of the model and create an animation for the electric field plot. So now I'll be opening the Ansys Electronics Desktop version 2022 R1. So first of all, we open the example here, file open example, and then we go to the HFSS RF microwave, and we click on this bandpass filter. And now we have a 3D model of the bandpass filter. We can see the project manager here and the model tree here. And you can see the fit pin 1 here, and fit pin 2 here. And we can see the resonator, which is the L, and all the resonator here. So now we already have a 3D geometries. Now we go to the boundaries. So for these boundaries, we don't need to assign anything here because we're already using the default boundaries, which is a perfect electric conductor, PEC. And then we go to excitation, and we can see the excitation here, the pin 1 and pin 2. You can see here the feed pin 1 T1 and feed pin T2. So which is the terminal 1 here and terminal 2 here. And how do we assign the excitation? So basically, we go to this, we click on the surface, right click on the excitation, we click on assign ports, and we're using the width port. You can see here, we're using the width port. And same goes to feed pin T2 on the other side here. And then after we set the citation, I forgot to mention about the solution the solution type. So to see the solution type, we go to HFSS, we click on solution type. You can see here for the solution type, we are using the HFSS with hybrid and arrays. You can click OK. After the excitation, we go to the mesh. For mesh, we don't need to assign any mesh operation because it already used the auto mesh setting. We can see in this initial mesh setting, we are using the auto mesh method. And for the mesh, we can set the mesh size to small or large. So basically, if we have a smaller mesh, it will give us an accurate result, but it will cost us more time to simulate it. While if we using a larger mesh size, we don't. It saves some time during the simulation, but the accuracy might differ. But in this simulation, this is just a simple high frequency simulation. So we'll be using the middle one, the middle mesh size, not too small and not too large. So okay. Now for after we setting the mesh, we go to the analysis setup. So to set the solution setup, we just right click on this analysis, add solution setup. We can you have an auto or advanced, but in this example, they already set us the simulation setup. So for this simulation setup, the frequency is 1.5 gigahertz with the maximum number of pulses 15 and maximum delta S 0.02. So click OK. And then after we set up the analysis, we need to analyze this. So to analyze the simulation, we simply go to the setup, right click it, and click on analyze. And we save it on the desktop. So for simulating this, it may take some time to simulate, but I've already have a soft version of this bandpass filter, which is this one. This is a soft version of bandpass filter. You can see in this result here, we can see the S parameter of the bandpass filter. You can see the red line here is the S11, which is the T1 and T1. So this is the gain for the S11 parameter. And for the green plot here, you can see the S12, the S parameter S12, and you can see the gain. This is the behavior of the bandpass filter, and you can see the red line is the input match S11. You can see only the middle signals pass through the filter. So after that, we can also see the electric field around inside the bandpass filter here. So to see this field, we select all this model. We right click this and plot field, and we have an electric, magnetic, also the J field and Q field here. So and we already have this E field simulated here. So how do we see the animation of this electric field? So to see the animation, we simply go to the magnitude electric one here. We right click this and we click on this animate. So, and then we click on OK. And we're creating frames for the animation. And we can see the animation for the electric field here. And then what we're going to do is to see the mesh of this to plot mesh on this geometry. And to see that, we simply go to field overlays, right click it and plot the mesh, and click on done. And now we can see the mesh plot of the geometry. And I think that's about it. This is how we simulate the bandpass filter. I hope you enjoy this. And if you have any question, you can ask me. And now I will give back the slides to Zulaika for further. So Zulaika, you can take the screen.
Okay, thank you very much, Mr. Farhan. Before we move to Q&A session, I will launch a poll. So please select the appropriate response and click submit. Now we move to Q&A session.
Any of you, if you have a question, you can just unmute your mic and see your question, or you can type on the chat box.
Yeah. Okay, so if you have a question for Mr. Farhan, you may raise your hand and turn on your microphone. So you can also submit a question via the chat features. And I will read your question to Mr. Farhan answer.
Okay, Zulaika, I think we have a question in the chat box here.
Yeah.
Does HFSS include the design tools? So, okay, before I answer that question, let me share back my screen. So, this is Ansys HFSS. To answer that, Ansys HFSS include design tools. You can see here, we have a draw tools here. You can draw line, SP line, arc. You can draw a simple rectangle, ellipse, circle, rectangular, polygon, box, cylinder, all here. This is all the design tool here. And you can also move, rotate, mirror, and unite. We have a Boolean tools here, unite, subtract, intersect, split, imprint. So it has a basic design tool, but if you have a difficult model, it's better for you to import from any CAD software into this into this HFSS design, into the 3D model. Thank you for asking. So is there any question for else?
Hello.
Yeah, hi.
Can HFSS import CAD file, and if it can, what CAD file format can import into HFSS?
Okay. To answer that, yes, HFSS can import CAD model if you have a complex design from CAD tools. Something that you cannot design using this HFSS design tool. So to import it, you can wait. So you can import. You can see here. You can import CAD model from EDB, ENF, AutoCAD here, ODB, Cadence, lead frame, all this you can import into Ansys HFSS. And yeah, if you want more like the extension list, you can see all this import file here. Yeah, this is all the full list of CAD model that can be imported into Ansys HFSS.
Okay, thank you.
Okay, does anyone have a question regarding this topic? Gently reminder, for those of you who have not yet responded to the poll, please go ahead and submit your response now because we will close the poll in a few moments. Does anyone have a question?
So if we don't have any more question, I think Zulaika, you can conclude this webinar if you want to.
Okay. So thank you again, Mr. Farhan, for answering those questions and for the great presentation. We appreciate you being here. Before we end, I would love to share with you about our upcoming event, which this is our upcoming event. Is Ansys Level Up 3.0. This event we will conduct on October 25. Be sure to mark your calendar to save the date, and the registration opens on July 2022. We also encourage you to connect with us on social media. If you have additional questions, you may contact us by email or by telephone. We are happy to provide additional support. Thank you all for attending. We hope you have learned and enjoyed this presentation. Have a nice day. Thank you again.
All right, thank you. Thank you all for coming.